In this video, we present the Mockingbird framework, which enables a targeted dynamic analysis of Java programs. The Mockingbird framework is an innovative integration of static and dynamic analysis tools. The collection of static analysis tools helps to identify and isolate potentially problematic code, while the newly introduced dynamic analysis tooling enables execution of just the relevant code. The framework earns its name from the testing community, which uses the term object mocking to refer to simulated objects that mimic the behavior of real objects in controlled ways. First, let's take a look at a motivating example. In this code, there is a division operation on line 23 with a potential division by zero error if all the letters of a pet's name are vowels. This is a problem that dynamic analysis fuzzing tools could find automatically, but the getValRatio method is not an isolated method in this program. Traditionally, this method could be tested by first constructing a pet object with the pet's name to be tested. However, in this example, the constructor has a costly sleep operation that will make testing each input expensive. Ideally, we could extract the relevant code from the getValRatio method while still maintaining control of its inputs. We solve this problem by using the Mockingbird framework to introduce mocked objects to strategically break a method's dependencies on the rest of the program. One way to break a dependency of the getValRatio method is to directly mock the object result of the getName method. This simple JSON configuration file instructs the Mockingbird framework to run the AFL fuzzer on the getValRatio method without invoking the pet constructor, while also translating AFL's driver outputs from a binary file to the string object returned by getName. Note that in this program, the isVal method is a pure method that does not mutate any pre-existing program state, which is why we have chosen not to mock the result of isVal in the configuration file, or any of the standard JDK methods for that matter. Another way to break a dependency of the getValRatio method is to allow getValRatio to call getName and then mock the name instance variable. Mockingbird is flexible and can handle the object mocking of parameters, return values, and global variables. The task of deciding how to break dependencies of relevant code is assisted by a collection of conservative static analysis tools in the Mockingbird framework's tool suite. Each configuration file is human-readable to allow for the refinement by human reasoning. One important refinement is that Mockingbird supports input generation constraints that can be used to embed domain knowledge and drive program execution in meaningful ways. Here we added a constraint to generate strings ranging in length from 1 to 10 characters because we didn't want AFL to generate strings that were too long. Given a configuration file, Mockingbird generates an AFL-compatible test harness and execution scripts, making the task of targeted dynamic analysis fuzzing extremely simple. Here's how we run AFL on the motivating example after configuring Mockingbird. That's all it takes. As a case study, we examine a DARPA STAC challenge application called Braid It, which we analyze for an algorithmic complexity vulnerability in space and time. Static analysis reveals that the application contains 51 loops, of which 29.4% of the loops are contained in a single class called plate. In particular, static analysis reveals that the normalize completely method contains a loop that is a candidate for an AC time vulnerability because its termination depends on a non-trivial property of the isReduced method. The isReduced method operates on an attacker-controlled global variable called intersections. The normalize completely method is also a candidate for an AC space vulnerability because both the normalize once and the free normalize methods write to the file system during each iteration of the loop. This makes the normalize completely method a prime candidate for a targeted dynamic analysis with the Mockingbird framework. After mocking the attacker-controlled input, it is a trivial task to run AFL. After running the generated AFL test harness for 20 hours, we found an input that caused an infinite loop, which exploited the AC vulnerability in space and time. Another 22 such inputs were found in an additional 19 hours of fuzzing. Interestingly, this application had been hardened against static and dynamic analysis techniques and was thought to not be vulnerable, yet the framework discovered the unintended vulnerability anyway. Using Mockingbird, we wrote a custom test harness to search for the smallest input that would reproduce the vulnerability. Using our domain knowledge, we further constrained the alphabet of our search strings to only alphabetic characters. The first result produced the smallest viable exploit in 20 minutes and reveals the underlying exploit invariant. The isReduced method returns false if the string contains an uppercase character of a lowercase character. This scheme is perfectly reasonable for ASCII, but there exists a small set of alphabetic Unicode characters whose uppercase character is their lowercase character. Given an odd number of these special Unicode characters, the string becomes irreducible and causes the denial of service vulnerability we observed earlier. Mockingbird is an open source project. Thanks for listening.